The life cycle of stars. Understanding the journey of our sun. The sun, the heart of our solar system, has shone brightly for billions of years, providing the energy that makes life possible on Earth. But like all stars, the sun also has a limited lifespan. In this chapter, we will explore the life cycle of stars, focusing on our sun and examining how it fits into the larger picture of stellar evolution. Understanding the sun's life cycle will help us prepare for the inevitable day when it passes through its final dramatic stages, changing not only itself, but the fate of our entire solar system. The history of the sun began about 4.6 billion years ago in a vast cloud of gas and dust, known as the molecular cloud or stellar nursery. This region was filled with hydrogen, helium, and small amounts of other elements, the raw materials for star formation. Over time, gravity began to pull these particles together, causing the cloud to collapse under its own weight. As the cloud collapsed, it began to heat up, forming a dense core known as a protostar. In the case of our sun, this process took tens of millions of years. Eventually, the core became hot enough to start nuclear fusion, the process in which hydrogen atoms fuse to form helium, releasing an enormous amount of energy. This energy is what powers stars and allows them to shine. Once nuclear fusion was fully underway, the sun entered what is known as the main sequence phase of its life. This is the longest and most stable period in a star's life cycle, during which it burns hydrogen in its core. Our sun has been in the main sequence phase for billions of years, providing a stable source of light and heat for our planet. Stars like our sun spend most of their lives in the main sequence phase. During this time, the inward gravitational forces are balanced by the outward pressure of nuclear fusion. This balance keeps the star stable and allows it to shine evenly for billions of years. Classified as a G-type main sequence star, or yellow dwarf, the sun is relatively small compared to other stars, yet incredibly powerful. Every second, the sun fuses about 600 million tons of hydrogen into helium, converting a small fraction of that mass into energy. This energy radiates into space as light and heat, reaching Earth and the other planets in our solar system. As the sun continues to burn hydrogen in its core, it gradually becomes hotter and brighter. In fact, the sun is about 30% brighter today than when it was formed. This slow increase in brightness will continue throughout the sun's main sequence phase, but this phase will not last forever. At some point, the sun will begin to exhaust its supply of hydrogen in its core. When this happens, the balance between gravity and fusion pressure will be disrupted, and the sun will undergo dramatic changes. This transition marks the end of the sun's main sequence phase and the beginning of its death. When the hydrogen in the core runs out, the core will contract under the force of gravity. However, the sun's outer layers will expand, and the sun will become much larger and cooler, turning into a red giant. This phase will begin in about 5 billion years, but its effects will be felt throughout the solar system, including on Earth. The red giant phase is one of the most important stages in a star's life cycle. As the core contracts and heats, hydrogen fusion will begin in a shell around the core, causing the sun's outer layers to expand dramatically. At its peak, the sun will grow to 100 times its current size, potentially engulfing the inner planets, including Mercury and Venus. As the sun expands, its surface temperature will drop, giving it a reddish hue, hence the name red giant. Despite its cooler surface, the sun's overall luminosity will increase significantly due to its much larger size. This increase in brightness will have catastrophic consequences for the remaining planets, including Earth. During the red giant phase, Earth's oceans will likely evaporate, and the atmosphere will be blown away by the intense heat and solar wind. Life as we know it will no longer be possible, and the surface of the planet will become a scorched, barren desert. Even if Earth is not directly engulfed by the expanding sun, the planet will become uninhabitable. As the sun continues to evolve as a red giant, the core becomes so hot and dense that it ignites a new round of nuclear fusion. This time, helium is fused into carbon and oxygen in a process known as helium fusion. This marks a new phase in the sun's life, but it will be relatively short compared to the billions of years spent in the main sequence phase. Helium fusion produces much less energy than hydrogen fusion, so the sun will not be able to sustain this process for long. After a few 100 million years, the sun will also exhaust its supply of helium, and the final stages of its life will begin. As the sun burns its remaining fuel, it will undergo a series of convulsions, shedding its outer layers into space. This ejected material will form a glowing shell of gas known as a planetary nebula, a beautiful and ephemeral phase that marks the end of the sun's active life. After the outer layers are shed, the sun's remaining core will be left as a white dwarf, a dense, hot remnant of the original star. A white dwarf is incredibly small, about the size of Earth, but contains most of the mass of the sun. Over time, this remnant will cool and fade, eventually becoming a cold, dark object known as a black dwarf. White dwarfs no longer undergo nuclear fusion, so they no longer produce new energy. Instead, they glow dimly with the residual heat left over from their previous life. The sun's transformation into a white dwarf will mark the true end of its stellar journey, leaving only a faintly glowing, slowly cooling core. Imagine standing on the surface of a distant planet, far from the tumult of our solar system, as the sun enters its red giant phase. From this distant vantage point, you'll see the sun grow to enormous size, its outer layers glowing a deep, fiery red. The once familiar yellow star now dominates the sky, casting a faint, reddish light across the surrounding space. As the sun expands, you can see the effects of its transformation on the inner planets. Mercury and Venus have already been swallowed up by the sun's outer layers, while Earth is a barren, lifeless rock whose oceans have long since evaporated. The once vibrant blue planet is now a scorched pile, slowly moving closer to the dying star. Eventually, after millions of years as a red giant, the sun's outer layers are ejected into space, forming a beautiful planetary nebula. The glowing shell of gas expands outwards, leaving behind the faintly glowing remnant of the sun, a white dwarf. From your distant planet, you witness the end of the sun's journey, a quiet, almost peaceful end to billions of years of stellar evolution. The sun's death is an inevitable part of its life cycle, but it is still billions of years in the future. When the time comes, the sun's transformation into a red giant, followed by its final phases as a white dwarf, will dramatically reshape our solar system. The Earth, although unlikely to be consumed by the sun, will become uninhabitable, marking the end of life as we know it. Understanding the sun's life cycle gives us insight into the fate of our planet and the universe as a whole. Stars are born, live, and die, but their remnants, be they in the form of white dwarfs, neutron stars, or black holes, continue to shape the cosmos. The death of the sun will be no exception, as its remnants will contribute to the ongoing history of stellar evolution. In the next chapter, we will explore what, if anything, can be done to prepare for the distant future when the sun begins to transform. Could humanity find a way to escape the dying solar system, or will we witness the end of our world from within? The future of humanity. Can we survive the end of the sun? After exploring the sun's life cycle and the inevitable changes, the question arises: what does this mean for humanity and the future of life on Earth? Will we have a chance to survive the sun's transformation into a red giant? Or are we doomed to see the end of our planet? In this chapter, we will look at possible future scenarios for humanity as the sun nears its end. Could we migrate to another planet or solar system? What technologies or advances would be necessary for our survival? Let's explore what the future might hold and how humanity might navigate the distant future of our solar system. As we discussed in the previous chapter, the expansion of the sun into a red giant will have devastating effects on Earth. Long before the sun reaches its maximum size, increasing heat and radiation will make the Earth uninhabitable. In fact, it is estimated that in about 1 billion years, the sun will be hot enough to vaporize Earth's oceans, turning the planet into a scorched wasteland. The atmosphere will be stripped away and all life forms will perish. This time frame, however unimaginably far in the future it may seem, still gives us a sense of urgency when it comes to thinking about our long-term survival. The first major obstacle for humanity will be dealing with the gradual increase in solar radiation over the next 1 billion years. But what about the near future? What steps could we take to protect ourselves, and where could we go if the Earth becomes uninhabitable? A possible solution to the problem of the sun's increasing heat is to move to another planet within our solar system. Mars is often considered the most promising candidate for human colonization, and many scientists and space agencies are already working on technologies to make a Mars colony a reality. Because Mars is farther from the sun than Earth, it would be less affected by the intense heat and radiation caused by the sun's transformation into a red giant. But Mars is not without its challenges either. Its thin atmosphere, lack of liquid water, and extreme temperatures make it a harsh environment for human life. Nevertheless, with advances in terraforming technology, humanity could succeed in transforming Mars into a more habitable planet. Terraforming Mars would involve changing its atmosphere to make it thicker and better at retaining heat, perhaps by releasing greenhouse gases or introducing microbes that can produce oxygen. Although this process would take centuries or millennia, it could provide humanity with a new home in the solar system, allowing us to escape the effects of the sun's changes. But Mars is only a temporary solution. As the sun continues to expand, Mars would eventually become too hot to support human life. This begs the question, could we leave our solar system entirely? To truly escape the sun's long-term fate, humanity would have to move beyond our solar system and orbit new stars. This idea, known as interstellar travel, has been a staple of science fiction for decades, but remains one of humanity's greatest technological challenges. The closest star to our solar system is Proxima Centauri, part of the Alpha Centauri star system, which is about 4.2 light-years away. This is relatively close in cosmic terms, but even with our most advanced propulsion technologies, it would take tens of thousands of years to reach this star using today's spacecraft. However, scientists are actively researching new forms of propulsion that could make interstellar travel a reality. Concepts such as nuclear fusion propulsion, antimatter propulsion, and light sails powered by lasers have been proposed as ways to achieve much faster travel times, which could shorten the journey to nearby stars to decades or centuries. An ambitious project called Breakthrough Starshot aims to send tiny, lightweight probes to Alpha Centauri using light sails powered by ground-based lasers. These probes could reach speeds of up to 20% of the speed of light and reach Alpha Centauri in just over 20 years. While this project is aimed at small probes and not human passengers, it still represents a significant step towards interstellar exploration. For humans to make the journey, we would need to develop much larger, more sustainable spacecraft that can support life for long periods of time. One possibility is the concept of a generation ship, a massive spaceship that could carry thousands of people on a journey lasting centuries. The ship's inhabitants would live their entire lives aboard, and future generations would continue the mission until they reach a new star system. Another possibility is cryogenic suspension, a technology that could make it possible to put humans into a state of deep hibernation to survive long space journeys. If perfected, this technique could significantly extend human lifespans and reduce the psychological challenges of long space travel. If humanity is to survive the end of the sun, we must find a new home among the stars. Fortunately, astronomers have already identified thousands of potential candidates in the form of exoplanets, planets that orbit other stars. The search for habitable exoplanets focuses on finding worlds that are in their star's habitable zone, where conditions are just right for liquid water to exist. One of the most promising discoveries in recent years is the TRAPPIST-1 system, located about 40 light-years from Earth. This system contains 7 Earth-sized planets, 3 of which are in the star's habitable zone. These planets could potentially have liquid water and other conditions necessary for life. In addition to the TRAPPIST-A system, astronomers on the Kepler and TESS missions have identified several other exoplanets that could be suitable for human habitation. Although these planets are well beyond our current reach, they represent potential targets for future interstellar missions. However, finding a habitable planet is only part of the challenge. Even if we discover a planet with Earth-like conditions, it might not immediately be suitable for human life. Terraforming or other forms of planetary remodeling may be necessary to make these distant worlds habitable. This would mean changing the planet's atmosphere, temperature, and surface conditions to create a stable environment for human life. Another potential solution to the Sun's death problem is to create artificial habitats that are completely independent of planetary surfaces. These habitats could exist in the form of giant space stations or even self-sustaining O'Neill cylinders, massive rotating structures that use centrifugal force to simulate gravity and provide housing for thousands or even millions of people. Artificial habitats would allow humanity to survive in environments where planets are unavailable or unsuitable for colonization. These habitats could be in the orbit of other stars or even within our own solar system, in areas safe from the effects of the Sun's transformation. One advantage of artificial habitats is that they could be designed to be completely self-sufficient, with closed-loop systems to recycle air, water, and nutrients. Advances in fusion energy could provide a nearly inexhaustible source of energy, allowing these habitats to operate for long periods of time independent of a nearby star. Imagine standing on a distant space station, watching Earth's final days unfold. By this time, humanity has already moved to Mars, other planets or artificial habitats, but Earth remains a symbol of our origins. As the Sun begins to swell into a red giant, watch from a distance as the once blue planet transforms into a scorched, lifeless world. The oceans evaporate, the atmosphere is stripped away, and the land becomes a barren desert. In the distance, the Sun shines hugely, casting a reddish glow across the solar system. But while the Earth dies, humanity lives on. You see the launch of massive interstellar ships heading to distant stars and new planets. These ships carry the hopes and dreams of future generations as humanity embarks on a journey to find a new home among the stars. This line of thought illustrates humanity's potential to survive the end of the Sun by adopting new technologies and exploring new frontiers. While Earth's fate is sealed, humanity's future may lie in the distant stars. The death of the Sun, even billions of years away, raises profound questions about the future of humanity and our place in the cosmos. Will we be able to survive the catastrophic changes in our solar system, or will we perish along with our home planet? The answers may lie in our ability to develop advanced technologies, explore new planets, and build sustainable habitats in space. Whether by colonizing Mars, reaching distant exoplanets, or building artificial worlds, humanity's future could be determined by our ability to adapt and evolve beyond Earth's boundaries. As we continue to explore the universe and push the boundaries of science and technology, we are reminded that our destiny is not limited to the solar system. The stars are calling, and with them the possibility of new homes, new challenges, and new beginnings. In the next chapter, we will examine the technological advances necessary for humanity to undertake interstellar travel. What innovations in propulsion, energy, and life support will be required for us to become a spacefaring civilization? The technological leap, preparing humanity for the journey to the stars. In the previous chapter, we looked at the challenges humanity will face if the sun turns into a red giant and makes the Earth uninhabitable. Whether we decide to migrate to Mars, colonize distant exoplanets, or build vast artificial habitats, one thing is clear: humanity's future depends on our ability to develop advanced technologies that will allow us to survive and thrive beyond Earth. In this chapter, we will examine the key technologies that will be necessary for humanity to undertake interstellar travel. From breakthroughs in propulsion technology and energy production to innovations in life support and sustainability, we take a look at how science and technology will shape the future of human space travel. The first and most obvious challenge to interstellar travel is the immense distance between stars. Even the closest star system, Alpha Centauri, is more than 4 light-years away. To put this in perspective, our fastest spacecraft, Voyager 1, launched in 1977, is currently traveling at about 17 kilometers per second, and it would take over 70,000 years to reach Alpha Centauri at that speed. So it is clear that if humanity wants to become an interstellar civilization, it will need to develop new propulsion technologies that can reach much higher speeds than our current chemical rockets. Several advanced propulsion concepts have been proposed that have the potential to revolutionize space travel. One of the most promising technologies for long-distance space travel is nuclear fusion propulsion. Fusion, the process that powers stars, involves fusing atomic nuclei together to release huge amounts of energy. Unlike nuclear fission, which is used in today's nuclear reactors, fusion produces much more energy and produces fewer harmful byproducts. A fusion-powered spacecraft could theoretically reach much higher speeds than chemical rockets. By using deuterium and tritium, isotopes of hydrogen, as fuel, a fusion engine could generate enough thrust to accelerate a spacecraft to a significant fraction of the speed of light. Several fusion propulsion concepts have been proposed, including inertial confinement fusion and magnetic confinement fusion. Inertial confinement fusion uses lasers to compress fuel pellets and heat them to extreme temperatures, causing them to fuse. Magnetic confinement fusion, on the other hand, uses strong magnetic fields to contain and control the fusion reaction. Although fusion propulsion is still in the experimental stage, research continues. Projects such as ITER, an international nuclear fusion research and engineering project, aim to demonstrate the feasibility of fusion as an energy source. If successful, Fusion drive could allow humanity to explore the stars much more efficiently, reducing travel times to nearby star systems from tens of thousands of years to just a few decades. Another advanced propulsion concept is antimatter propulsion, which could theoretically offer the highest energy efficiency of any propulsion system. When matter and antimatter collide, they destroy each other, releasing an enormous amount of energy. In fact, antimatter reactions are about 100 times more efficient than nuclear fusion. Antimatter is the mirror image of normal matter, with the particles carrying opposite charges. For example, the antimatter counterpart of an electron is the positron, which carries a positive charge instead of a negative one. In an antimatter drive, antimatter particles could be combined with normal matter to produce energy, which would then be used to produce thrust. Although antimatter propulsion offers great potential, it also presents significant challenges. Currently, producing even tiny amounts of antimatter is extremely difficult and expensive. Particle accelerators like the Large Hadron Collider can produce antimatter, but only in tiny amounts. Storing antimatter is also a challenge, as it must be isolated from normal matter to prevent premature annihilation. Despite these hurdles, antimatter propulsion remains one of the most exciting and speculative technologies for future space travel. If scientists can produce and store antimatter efficiently, it could revolutionize interstellar space travel, allowing spacecraft to reach distant stars in a few years or even months. Another promising concept for interstellar travel is the use of light sails, a technology that harnesses the power of light or lasers to propel a spacecraft. A light sail works by bouncing photons, light particles, off a large reflective surface, creating a small but continuous force that can accelerate the spacecraft over time. Unlike chemical rockets, which require fuel, light sails do not require onboard fuel. Instead, they are powered by the momentum of the photons hitting the sail. In space, where there is no atmosphere slowing the spacecraft, this continuous acceleration can eventually bring the spacecraft to a significant fraction of the speed of light. One of the most ambitious projects using light sails is Breakthrough Starshot, a research initiative that aims to send tiny, lightweight spacecraft with light sails to the Alpha Centauri star system, powered by powerful ground-based lasers. The goal is to accelerate these miniature spacecraft to speeds of up to 20% of the speed of light, allowing them to reach Alpha Centauri in about 20 years. While Breakthrough Starshot is aimed at small, unmanned probes, the same technology could potentially be scaled up to carry human passengers. Light sails represent an exciting possibility for interstellar travel, offering a method of propulsion that does not rely on large amounts of fuel and could reach distant star systems within a human lifetime. However, traveling to the stars is only part of the challenge. Once humanity undertakes interstellar travel, we will need to develop advanced life support systems that can sustain human life for extended periods of time. Space is a harsh and unforgiving environment, with no access to the resources we on Earth rely on to survive. To be successful in long-duration space travel, we must create closed-loop systems that can recycle air, water, and food indefinitely. One of the biggest challenges is the development of oxygen production systems. On Earth, plants produce oxygen through photosynthesis, but in space we need artificial methods to produce oxygen. Current life support systems, such as those used on the International Space Station, ISS, use electrolysis to split water molecules into hydrogen and oxygen, but this process requires a continuous supply of water. To create truly sustainable life support systems, scientists are exploring the use of bioregenerative life support, which allows plants and other organisms to grow in space to recycle waste products, produce oxygen, and provide food. Experiments like NASA's Veggie project, which grows crops on the ISS, are paving the way for future space farms that could be essential for long-duration space missions. In addition to oxygen and food production, maintaining a stable temperature and radiation protection is critical to human survival in space. Spacecraft and habitats must be equipped with advanced temperature control systems to regulate temperature, and protective devices must be developed to protect against cosmic and solar radiation. One of the biggest challenges in long-term space travel is the effects of microgravity on the human body. Prolonged exposure to microgravity can lead to muscle atrophy, loss of bone density, and other health problems. To solve this problem, scientists are exploring ways to create artificial gravity in spacecraft and habitats. One of the most promising methods for creating artificial gravity is the use of centrifugal force. The rotation of a spacecraft or space station can create a force similar to gravity, pulling objects and people toward the outer walls of the structure. This concept has been popularized in science fiction, but is also a serious area of research for future space missions. Rotating habitats, such as O'Neill cylinders or Bernal spheres, could provide artificial gravity for long-duration space flights, allowing people to live and work in space without suffering the negative effects of microgravity. Although building large rotating structures poses significant technical challenges, this could be a key technology for future interstellar missions. Energy is another critical factor for interstellar travel. Spacecraft and space habitats require large amounts of energy to power life support systems, propulsion, and other essential functions. One of the most promising technologies for generating energy in space is fusion energy, which could provide a nearly unlimited source of energy for long-duration missions. Fusion energy, as already mentioned in connection with propulsion systems, is based on the fusion of atomic nuclei to release energy. If humanity manages to develop viable fusion reactors, they could provide spacecraft with the energy necessary to enable long-term missions, power advanced life support systems, and even power the spacecraft itself. Another possible energy source is solar energy, which could be generated through large arrays of solar panels. In the outer regions of the solar system, where sunlight is much weaker, spacecraft could use nuclear energy sources, such as radioisotopic thermoelectric generators, RTGs, which convert the heat from radioactive decay into electricity. For interstellar travel where traditional solar power may not be practical, researchers are also exploring the use of antimatter reactors and other advanced energy production methods. These technologies could one day provide the energy needed for humanity's travel to distant star systems. Imagine standing on the edge of a massive space station and watching humanity's first interstellar spacecraft being built. The ship, a colossal fusion-powered vehicle, is designed to carry thousands of passengers on a multi-generational journey to a distant star system. From your vantage point, you can see the rotating sections of the ship that will create artificial gravity for the crew and passengers. Vast arrays of solar panels and fusion reactors provide energy, while advanced life support systems recycle air, water, and nutrients to sustain life for centuries. As the ship prepares to launch, you realize that this moment represents the culmination of centuries of scientific and technological progress. Humanity is no longer tied to Earth or even the solar system. The stars are within reach, and the future of our species lies beneath them. This thought experiment reminds us of the incredible challenges and opportunities that lie ahead. With the right technologies, humanity could one day travel to the stars, ensuring the survival of our species for millennia. The journey to the stars will require a technological leap, the likes of which humanity has never undertaken before. From advanced propulsion systems to sustainable life support and energy production, the challenges are immense, but so are the rewards. As we advance these technologies, we move closer to a future where interstellar travel is possible, and humanity can escape the confines of our dying sun. Whether through fusion drives, antimatter engines, or light sails, the stars are no longer out of reach. In the next chapter, we will examine humanity's future once we reach the stars. What new challenges and opportunities will we experience as we establish colonies in distant star systems? How will living in the cosmos change our understanding of ourselves and our place in the universe? Humanity under the stars. Life in distant star systems. In previous chapters, we have examined the technologies necessary to enable humanity to escape the inevitable destruction of our sun and travel to the distant stars. But arriving at the stars is just the beginning. As we reach new star systems, we will face an entirely new set of challenges and opportunities as we establish colonies on distant worlds or in artificial habitats. In this chapter, we will consider what life might be like for humans in these far-flung regions of the galaxy. How will we adapt to new environments, and what social, cultural, and scientific changes might occur as we settle among the stars? As we engage in this thought experiment, we will explore both the potential and risks of a multiplanetary species. When we reach a new star system, the first challenge will be to find or create a habitat that supports humanity's survival. While some exoplanets may lie in their star's habitable zone, where liquid water and Earth-like conditions could exist, it's unlikely we'll immediately find a planet perfect for human habitation. One possible solution is terraforming, the process of transforming an alien planet into an Earth-like environment. Terraforming could involve changing a planet's atmosphere, temperature, and surface conditions to make it habitable for humans. On a planet like Mars, this could mean releasing greenhouse gases to thicken the atmosphere and increase temperatures, or introducing genetically modified plants and microbes to produce oxygen. However, terraforming is a lengthy and resource-intensive process. It could take centuries or even millennia to fully transform a planet into a habitable environment. In the meantime, humans would likely rely on artificial habitats like biospheres or domed cities to survive. Biospheres are closed ecosystems that recycle air, water, and nutrients, creating a self-sustaining environment for human life. These habitats would have to be carefully constructed to maintain the correct balance of gases, humidity, and temperature. They could be built on the surface of planets, moons, or even in free-floating space colonies. A more radical approach would be to genetically modify humans so that they can survive in different planetary environments. This could mean changing our biology so that we can handle different levels of gravity, radiation, or atmospheric composition. While this idea remains speculative, advances in genetic engineering and synthetic biology could one day allow humans to adapt to a variety of alien environments without relying on extensive terraforming. The transition from a single planetary to a multiplanetary species will profoundly change not only our technology, but also our society, culture, and identity. Life in distant star systems, isolated from Earth, could lead to the emergence of new cultures and social structures. One of the most immediate changes will be the experience of isolation. Communication between star systems is limited by the speed of light, meaning even a message to the nearest star, Alpha Centauri, takes more than 4 years to arrive. As a result, colonies in distant star systems would become increasingly autonomous, developing their own cultures, languages, and systems of government. Over time, these distant colonies could become so culturally different from Earth that they could be considered entirely new civilizations. We could see the emergence of planetary nations, each with their own unique way of life, shaped by the environment and challenges of their homeworld. The laws, customs, and technologies of a colony on a high-gravity planet could be very different from those of a space station orbiting a gas giant or an artificial habitat in deep space. This isolation could also lead to speciation, where people in different environments diverge physically and biologically over thousands or millions of years. For example, on a planet with higher gravity, shorter, stockier bodies could evolve to withstand the increased pressure on bones and muscles. Meanwhile, people living in space for generations could develop longer limbs or changes in bone density due to microgravity. Beyond the physical and technological challenges, the psychological impact of long-term space colonization should not be underestimated. Living in isolated, enclosed environments with limited access to natural light and fresh air can place a significant strain on mental health. Astronauts on the International Space Station, ISS, already face these challenges during their relatively short missions. They experience disorientation due to the lack of gravity, disrupted sleep patterns due to the rapid day-night cycles in orbit, and feelings of isolation from living in a small, enclosed space. These challenges would be magnified in the context of interstellar travel or life on distant worlds. Maintaining mental health will be a critical priority for future space colonies. This could include creating artificial environments that simulate natural terrestrial conditions, such as virtual landscapes or indoor parks with artificial sunlight. Psychological support services, including therapy and community building activities, will also be crucial in helping colonists deal with the stresses of living in a strange, isolated environment. The feeling of alienation from Earth, the homeworld, could also be profound. After several generations, colonists in distant star systems may no longer feel strongly connected to Earth. They could develop a new identity more rooted in their new homeworld than in the planet on which humanity originated. This shift in identity could cause tensions between Earth and its colonies as the needs and priorities of different planets drift apart over time. What happens when we are not alone? One of the most intriguing possibilities for colonizing distant star systems is the potential discovery of extraterrestrial life. Although scientists have not yet found clear evidence of life outside Earth, given the vastness of the universe, it seems likely that we are not alone. As humanity explores new star systems, we may encounter microbial life forms, complex ecosystems, or even intelligent alien civilizations. If we find extraterrestrial life, it will have profound implications for science, philosophy, and religion. The discovery of microbial life on an exoplanet could provide clues to the origins of life on Earth, while the existence of intelligent alien species would challenge our understanding of what it means to be human. However, the discovery of extraterrestrial life also raises ethical and practical questions. How would we interact with alien life forms, especially if they are intelligent? Should we try to communicate with them or avoid contact altogether to minimize potential risks? Could our presence on a planet with alien life disrupt its natural ecosystems and cause unintended consequences? The possibility of xenobiology, the study of extraterrestrial life, will become a central focus of scientific research in future space colonies. Understanding how life evolves under different environmental conditions will not only expand our knowledge of biology, but also help us make informed decisions about how we interact with extraterrestrial ecosystems. As humanity expands into space, artificial intelligence, AI, and robotics will play an increasingly important role in all aspects of space exploration and colonization. From managing life support systems to building habitats, AI and robots will be critical to overcoming the challenges of living in space. A major advantage of AI is its ability to process huge amounts of data quickly and efficiently. AI systems could be used to monitor the health of spacecraft and habitats, identify potential problems before they become critical, and optimize the use of resources such as energy, water, and oxygen. Additionally, AI could aid in navigation and help interstellar ships chart their course through the galaxy. Robots will also be crucial for tasks that are too dangerous or labor-intensive for humans. Autonomous robots could build colonies on distant planets, mine resources from asteroids, and explore dangerous environments such as the surface of a gas giant or the frozen oceans of an ice moon. By taking on these tasks, robots enable people to focus on scientific research, exploration, and community building. The relationship between humans and AI is likely to continue to evolve as we become increasingly reliant on these technologies. In some cases, AI systems could become so advanced that they take on leadership roles in space colonies, making decisions about resource management and long-term planning. This raises important ethical questions about the balance of power between humans and machines and how much autonomy we should grant artificial intelligence. Imagine a child born on an exoplanet in a distant star system, far from Earth. This child grows up in a biosphere, or domed city, surrounded by the technology and infrastructure that keeps the colony running. The child has never seen Earth and has only heard stories about the home planet from his parents and grandparents. As this child grows, he or she develops a unique sense of identity shaped by the environment and culture of the colony. It learns about the local ecosystem, studies the alien landscape outside the dome, and dreams of one day exploring the surface of its new world. For this child, Earth is not the center of the universe. His exoplanet home is. This thought experiment illustrates the transformative nature of space colonization. As humans settle on distant planets, our sense of identity, our culture, and our connection to Earth will change. We will no longer be bound to a single planet, and the concept of home will take on new meanings in the context of the vast, interconnected galaxy. The evolution into a multiplanetary species will bring both incredible opportunities and unprecedented challenges. As we colonize new star systems, we will need to adapt to alien environments, create self-sustaining habitats, and redefine our cultural identities. The isolation of life in distant star systems, coupled with the possible discovery of extraterrestrial life, will fundamentally change our understanding of ourselves and our place in the universe. Artificial intelligence, robotics, and genetic engineering will play central roles in helping humanity thrive in these new environments. But we must also keep in mind the ethical implications of these technologies. As we continue our journey into the cosmos, we will face profound questions about the nature of life, the limits of human adaptability, and the future of our species. In the next chapter, we will examine the scientific, philosophical, and ethical implications of living in a multiverse. Could there be parallel universes with different physical laws and realities? And what does that mean for our understanding of existence? The multiverse, exploring parallel universes and alternative realities. As humanity expands deeper into the cosmos and becomes a multiplanetary species, we are constantly expanding the boundaries of our understanding of space, time, and existence. One of the most fascinating and intellectually challenging concepts in modern physics is the idea of the multiverse, the possibility that our universe is just one of many, with each universe having its own unique physical laws, constants, and realities. In this chapter, we will explore the scientific basis of multiverse theory, the different types of multiverses that have been proposed, and the philosophical and ethical implications of living in a multiverse. Could there be parallel versions of ourselves living in alternate realities? What would it mean if we could travel between universes? And how does the multiverse fit into the hidden code of existence? The concept of the multiverse comes from several areas of modern physics, including quantum mechanics, cosmology, and string theory. While the idea of multiple universes may seem like science fiction, it is rooted in serious scientific theories that attempt to explain the nature of reality at the most fundamental level. One of the main ideas that leads to the concept of the multiverse comes from quantum mechanics, specifically the phenomenon of superposition. In quantum mechanics, particles can exist in multiple states at the same time, and only when we observe the particle does it choose a specific state. This idea is most famously illustrated by Schrödinger's cat, a thought experiment in which the cat is simultaneously alive and dead until observed. The many worlds interpretation of quantum mechanics goes one step further by proposing that every time a quantum event with multiple possible outcomes occurs, the universe splits into multiple branches, with each branch representing a different outcome. In this interpretation, there could be an infinite number of parallel universes, each representing a different sequence of events. In some of these universes, you may have made different choices in life, resulting in completely different outcomes. On a larger scale, the concept of the multiverse is also supported by cosmology. The inflation model of the universe, which describes how the universe expanded rapidly in the moments after the Big Bang, suggests that there may be other pocket universes in different regions of space. These pocket universes could have different physical laws and constants, and thus have completely different realities than our own. Physicists have proposed several different models of the multiverse, each describing a different way multiple universes could exist. Let's explore some of the most prominent types of multiverses. The Level 1 multiverse is the simplest form of multiverse and arises naturally from the idea that the universe is infinite. In this model, there are regions of space beyond what we can observe with our telescopes. These regions are so far away that light from them has not yet reached us since the Big Bang. Since the universe is infinite, there could be infinite variations in the arrangement of matter in these distant regions, creating a type of parallel universe. However, the physical laws in these regions would be the same as in our observable universe. The Level 2 multiverse is the result of the inflation theory of cosmology. In this model, different regions of space experience inflation at different rates, leading to the formation of separate bubble universes. Each bubble universe could have different physical constants, making them very different from each other. In some bubble universes, stars and galaxies might never form, while in others, the laws of physics might allow for completely different forms of matter and energy. The Level 3 multiverse arises from the many worlds interpretation of quantum mechanics that we have already discussed. In this model, the universe splits into multiple branches each time a quantum event occurs, with each branch representing a different possible outcome. In one branch, you might have chosen to study physics instead of biology, while in another, the outcome of a war might be different. These parallel universes all exist at the same time, but are inaccessible to each other. The Level 4 multiverse is the most speculative and far-reaching of all multiverse models. It states that all possible mathematical structures correspond to their own physical realities. In this view, every universe exists that can be described by a consistent set of mathematical rules. This means that universes with completely different dimensions, physical laws, and even forms of consciousness could exist in the Level 4 multiverse. It's a mind-boggling concept that pushes the boundaries of our understanding of reality. Imagine for a moment that you could somehow travel between the parallel universes in the Level 3 multiverse. In one of these universes, you meet a version of yourself that has made different choices in life. Maybe in this parallel universe you chose a different career, lived in a different country, or had different relationships. When you interact with this parallel version of yourself, you begin to see how small decisions can create large waves of change. The alternate version of you is similar to you, but at the same time, different in subtle ways. Her experiences have made her a person both familiar and strange. This thought experiment raises fascinating questions about identity, free will, and the nature of choice. If every possible version of you exists in some branch of the multiverse, what does that say about the choices you make in that universe? Are you truly free to make decisions, or do all possible outcomes play out somewhere in the multiverse? The idea of a multiverse raises profound philosophical questions about the nature of reality and our place in it. If there are infinite versions of the universe, with infinite versions of ourselves, does that mean our actions in that universe are less significant? If every possible outcome occurs somewhere in the multiverse, what does that mean for concepts like morality, free will, and personal responsibility? One possible interpretation is that the multiverse challenges the idea of absolute reality. If there are infinite versions of reality, then our universe is just one of many, and our experiences are just one possible path among countless others. This could lead to a kind of existential humility, recognizing that our universe is not necessarily unique or special. However, the multiverse could also provide a sense of comfort. If every possible version of ourselves exists somewhere in the multiverse, then no path is ever truly closed. Every possibility is realized in some branch of the multiverse, meaning that every dream, goal, and potential future exists in some form, even if we don't experience it in our current universe. The multiverse also raises ethical questions about how we would interact with other possible realities. If we could travel between universes, how would we treat the inhabitants of those worlds? Would we see them as equals, or just alternative versions of ourselves? These questions challenge our understanding of empathy, identity, and the value of life. Although the multiverse theory is fascinating, it faces a major challenge: the lack of direct observational evidence. Because the other universes are either too far away or exist in separate dimensions, we currently have no way to observe them directly. This makes the multiverse hypothesis difficult to test using traditional scientific methods. However, scientists are exploring indirect ways to test the multiverse theory. For example, Some physicists believe that if our universe had collided with another bubble universe during the early stages of inflation, it could have left detectable traces in the cosmic background radiation, CMB, the afterglow of the Big Bang. By studying the CMB in detail, we could find evidence of such a collision, which would support the existence of other universes. Another possible research approach is the study of black holes. Some physicists have suggested that black holes could act as gateways to other universes. If matter falls into a black hole, it could be transported to another region of space-time or even an entirely different universe. Although this idea remains speculative, it is an intriguing possibility that could one day be tested through observations of black holes and gravitational waves. The multiverse, if it exists, represents a new layer of the hidden code that governs the universe. It suggests that the physical laws we observe in our universe are just one possible expression of the deeper mathematical structures that underpin all of reality. In the multiverse, each possible universe follows its own rules, creating a vast and diverse landscape of realities. Understanding the multiverse could also provide answers to some of the most fundamental questions in cosmology, such as why the physical constants in our universe are so finely tuned that they allow life to exist. In the multiverse, the fine-tuning of our universe could simply be the result of chance. With an infinite number of universes, it is inevitable that some will have the right conditions for life to emerge. However, the multiverse also challenges our ability to fully understand the nature of reality. If there are infinite versions of the universe, then our knowledge of the cosmos is inherently limited. We may never be able to observe or interact with the vast majority of these other universes, forcing us to reflect on the true extent of existence. The multiverse is one of the most intellectually stimulating ideas in modern science, challenging our understanding of reality and raising profound questions about the nature of existence. Although the idea of parallel universes and alternate realities may seem speculative, it is anchored in serious scientific theories and could one day provide answers to some of the most fundamental mysteries of the cosmos. As we continue to explore the universe and push the boundaries of science and technology, the possibility of a multiverse reminds us that the cosmos is far more complex and mysterious than we ever imagined. Whether or not we can ever prove the existence of other universes, the multiverse forces us to question the limits of our knowledge and consider the infinite possibilities that lie beyond our own reality. In the next chapter, we will examine one of the greatest mysteries of the universe, the origin of life. What are the conditions necessary for life to arise, and could life be widespread in the cosmos? We will delve into the science of astrobiology and the search for extraterrestrial life. The origin of life, deciphering the secret of life in the cosmos. The origin of life is one of science's most profound and enduring mysteries. How did life begin on Earth? And could the same process have occurred elsewhere in the universe? As we move deeper into the cosmos and consider the possibility of extraterrestrial life, understanding the conditions that lead to the emergence of life becomes increasingly important. In this chapter, we will explore the science behind the origin of life on Earth, from the early conditions of our planet to the complex processes that led to the first living things. We'll also explore the possibility of life elsewhere in the universe by looking at the factors that make a planet habitable and the methods scientists use to search for life beyond Earth. Finally, we will consider the philosophical and ethical implications of the discovery of life elsewhere in the cosmos. To understand how life might arise elsewhere in the universe, we must first understand how life began on Earth. The earliest evidence of life on Earth dates back about 3.5 billion years, but the planet itself is much older, forming about 4.5 billion years ago. In its early days, Earth was a very different place than the one we know today. It was a chaotic world filled with volcanic activity, frequent asteroid impacts, and extreme environmental conditions. Despite these challenges, early Earth had several crucial ingredients necessary for life: liquid water, a stable atmosphere, and an abundant supply of chemical elements. The first forms of life are thought to have originated in the oceans, where water provided a stable environment for the complex chemical reactions necessary for life. A leading theory on the origin of life is the so-called primordial soup hypothesis. This theory suggests that the early oceans were filled with a rich mix of organic molecules created by chemical reactions, powered by energy sources such as lightning or ultraviolet radiation from the sun. Over time, these molecules combined to form more complex compounds, eventually leading to the first self-replicating molecules, the precursors of life. Another theory, known as the hydrothermal vent hypothesis, proposes that life may have originated in the depths of the ocean, near hydrothermal vents on the seafloor. These springs, releasing hot, mineral-rich water, could have provided the energy and chemical conditions necessary for life to emerge. The discovery of ecosystems around hydrothermal vents where life thrives without sunlight supports this idea and suggests that life can exist in a variety of extreme environments. The transition from simple chemical compounds to complex, self-replicating organisms is one of the greatest mysteries in biology. At the heart of this transition is the development of biomolecules, the complex molecules that make up living organisms. These include nucleic acids, such as DNA and RNA, that store genetic information, proteins that perform a variety of functions in cells, and lipids that form the membranes that protect cells from their environment. The first step in the origin of life was probably the formation of simple biomolecules that may have been synthesized from the organic compounds in the early Earth environment. These molecules then had to organize themselves into more complex structures capable of carrying out the functions necessary for life, such as metabolism, the process of converting energy, and replication. One of the central questions in studying the origin of life is how these molecules became able to replicate themselves. In modern organisms, DNA carries the instructions for building proteins, but proteins are necessary to replicate DNA. This creates a chicken and egg problem. How could life begin if both DNA and proteins are needed for replication? One possible solution to this problem is the RNA world hypothesis, which states that RNA, a molecule similar to DNA, may have been the first self-replicating molecule. RNA, like DNA, can store genetic information, but it can also act as a catalyst for chemical reactions, meaning it could have played a dual role in the early stages of life. Over time, as life became more complex, DNA and proteins may have taken over these functions. Once self-replicating molecules emerged, they would have succumbed to natural selection, the process by which organisms better adapted to their environment are more likely to survive and reproduce. This process would have driven the evolution of more complex life forms, eventually leading to the diversity of life we see today. Are we really alone? As we learn more about the origin of life on Earth, we can apply this knowledge to the search for life elsewhere in the universe. Scientists are particularly interested in finding planets or moons that have the right conditions for life: liquid water, a stable atmosphere, and the presence of organic molecules. One of the key factors in the search for extraterrestrial life is the habitable zone, also known as the Goldilocks zone. This is the area around a star where temperatures are just right for liquid water to exist. If a planet is too close to its star, the water evaporates, and if it is too far away, the water freezes. Planets that are in the habitable zone are prime candidates for the search for life. So far, astronomers have discovered thousands of exoplanets, planets that orbit stars outside our solar system. Many of these exoplanets are in the habitable zone of their star, raising the possibility that they could harbor life. One of the most exciting discoveries is the TRAPPIST-A system, which contains 7 Earth-sized planets, 3 of which are in the habitable zone. These planets are among the best candidates for the search for life outside our solar system. In addition to searching for planets, scientists are also looking for biosignatures, or signs of life, in the atmospheres of distant worlds. By studying the light that passes through an exoplanet's atmosphere, astronomers can detect the presence of gases such as oxygen and methane produced by living organisms on Earth. Detecting these gases on an exoplanet could be a strong indication that life exists there. Closer to home, scientists are also investigating the possibility of life on moons in our own solar system. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, both have subsurface oceans beneath their icy crusts. These oceans are kept warm by the tidal forces of their parent planets and may contain the conditions necessary for life. In recent years, missions such as NASA's Europa Clipper mission and the Cassini spacecraft have provided exciting evidence of water vapor columns and organic molecules on these moons, suggesting they could be promising places to search for microbial life. One of the most important discoveries in the search for extraterrestrial life is the realization that life can exist in a variety of extreme environments. On Earth, we have found life in places that were once considered completely uninhabitable, such as deep hydrothermal vents, acidic hot springs, and even rocks located kilometers below the Earth's surface. These organisms, known as extremophiles, have adapted to survive in extreme conditions such as extreme heat, cold, pressure, acid, or radiation. Their existence challenges our traditional ideas about what makes a planet or moon habitable and expands the range of environments in which life could potentially exist. For example, Tardigrades, tiny microscopic creatures known for their incredible resilience, can survive in the vacuum of space, extreme temperatures, and high levels of radiation. Their ability to survive such harsh conditions suggests that life could survive in environments much more extreme than we previously thought possible. This discovery has important implications for the search for life beyond Earth. It means life could exist in places we've previously overlooked, such as beneath the icy surface of Mars or in the subsurface oceans of moons like Europa and Enceladus. It also opens up the possibility that life could exist in completely different forms than what we know on Earth. The discovery of life beyond Earth would have profound implications for our understanding of the universe and our place in it. For centuries, people have wondered whether we are alone in the cosmos, and evidence of even the simplest life forms elsewhere would fundamentally change our perspective on the uniqueness of life. Philosophically, the existence of extraterrestrial life would challenge many of our assumptions about the nature of life and the necessary conditions for its existence. It would force us to rethink the idea that Earth is the only privileged cradle of life and raise new questions about the potential diversity of life forms in the universe. If we discovered intelligent alien life, the implications would be even more profound. How would we communicate with these beings? What ethical obligations would we have towards them? And how would such a discovery affect our view of humanity's role in the universe? There are also ethical considerations regarding our search for life. As we explore other planets and moons, we must be careful not to contaminate these environments with Earth-based microbes that could disrupt potential alien ecosystems. This is called planetary protection and is an important aspect of missions to Mars, Europa, and other potentially habitable worlds. Imagine if humanity had just discovered microbial life beneath the icy surface of Europa. After years of research and exploration, we find a thriving ecosystem of microorganisms living in the ocean, supported by the heat from hydrothermal vents deep beneath the surface. The discovery shocked the scientific community and the world. For the first time, we have definitive proof that life exists beyond Earth. Governments, scientists, and the public are debating the ethical implications of exploring this extraterrestrial life. Should we continue to explore and potentially disrupt this ecosystem, or should we leave it untouched? At the same time, the discovery raises new questions about the possibility of more complex life elsewhere in the universe. If life can exist on Europa, could it also exist on distant exoplanets? What would it mean for humanity if we discovered intelligent alien civilizations? This thought experiment illustrates the excitement and uncertainty that would accompany the discovery of extraterrestrial life. It reminds us that while we eagerly search for life beyond Earth, we must also be prepared for the profound ethical and philosophical challenges such a discovery would pose. The search for the origins of life and the possibility of life beyond Earth is one of the most exciting and important scientific endeavors of our time. By understanding how life began on Earth, we can gain insight into the conditions that allow life to thrive elsewhere in the universe. As we continue to explore our own solar system and study distant exoplanets, the possibility of discovering extraterrestrial life becomes more real. Whether we find microbial life in the oceans of Europa or detect biosignatures on a distant exoplanet, the discovery of life beyond Earth would be one of the most significant moments in human history. In the next chapter, we will explore another profound question. What is the ultimate fate of the universe? Will the cosmos continue to expand forever, or will it eventually collapse in a cosmic catastrophe? Join us as we delve into the science of cosmic fate and the future of the universe. The fate of the universe. How will it all end? As we continue our exploration of the cosmos, we are drawn to one of the most profound questions in all of science. What is the ultimate fate of the universe? Will it expand forever, becoming colder and emptier over time, or will it eventually contract back in on itself and end in a catastrophic event? To understand the future of the universe, we must consider the forces shaping its cosmic evolution, including dark energy, gravity, and the nature of space-time itself. In this chapter, we will explore the various scenarios for the end of the universe, from the Great Freeze and Great Ripping to the Great Collapse, and even the speculative possibility of a Great Rebound. Each of these theories offers a unique perspective on the future of the cosmos and raises fascinating questions about the nature of time, space, and existence. To understand the future of the universe, we must first consider how it is evolving today. Since the discovery of the Big Bang in the early 20th century, scientists have known that the universe is expanding. In fact, distant galaxies are moving away from us at incredible speeds, and the further away they are, the faster they are moving away. This relationship is described by Hubble's law, which shows that the universe has been expanding since its birth. But what will happen to this expansion in the future? Will it continue indefinitely, or will it slow down and eventually reverse? The answer depends on several key factors, including the amount of matter and energy in the universe and the nature of dark energy, the mysterious force that drives the accelerated expansion of space. One of the most surprising discoveries in modern cosmology is that the expansion of the universe is not slowing down, as once thought, but is actually accelerating. This discovery, made in the late 1990s by two independent teams of astronomers, fundamentally changed our understanding of cosmic evolution. The force responsible for this acceleration is called dark energy, and it currently accounts for about 70% of the universe's total energy content. Dark energy is one of science's greatest mysteries. We don't yet know what it is, how it works, or why it exists. What we do know is that it acts as a kind of repulsive force, pushing galaxies apart and accelerating the expansion of space. If dark energy continues to dominate the universe, it will have a profound impact on the future of the cosmos. The nature of dark energy is key to understanding the fate of the universe. If dark energy remains constant over time, the universe could expand forever, leading to a scenario known as the Great Freeze. However, if the strength or behavior of dark energy changes, other outcomes could occur, such as the Great Ripping or the Great Collapse. The most widely accepted theory about the fate of the universe is the Great Freeze, also known as the heat death of the universe. In this scenario, the universe expands forever, powered by dark energy. But as it expands, it gets colder and darker. As galaxies move further and further apart, the space between them increases and the density of matter decreases. Over billions and trillions of years, stars will exhaust their fuel and eventually die, leaving behind cold remnants like white dwarfs, neutron stars, and black holes. New stars will no longer form, and the galaxies will become dimmer and dimmer until they are finally completely dark. Eventually, even the black holes will evaporate due to a process known as Hawking radiation, a phenomenon that Stephen Hawking predicted in the 1970s. This radiation causes black holes to lose mass and energy over time, slowly shrinking until they disappear completely. In the final stages of the Great Freeze, the universe will be an empty, dark void, with no stars, planets, or galaxies. All that remains are isolated particles drifting through an ever-expanding, increasingly cold universe. This is the final end of entropy, where all energy is evenly distributed and no more work can be done. Time itself may lose its meaning, as there are no longer any events or processes to mark its passage. The Great Freeze is a bleak vision of the universe's future, but it is the most likely outcome if dark energy remains constant and expansion continues indefinitely. While the Great Freeze is the most widely accepted theory, there is another, more violent possibility for the end of the universe: the Great Rip. This scenario depends on the nature of dark energy, particularly whether its strength increases over time. In the Great Rift, dark energy grows stronger as the universe expands, eventually overcoming the gravitational and electromagnetic forces that hold galaxies, stars, planets, and even atoms together. As a result, the fabric of space-time itself is torn apart. In the final moments of the Great Rip, the galaxies would be torn apart first, followed by the individual stars and planets. Eventually, if the strength of dark energy reaches extreme levels, even atoms and subatomic particles would be torn apart, leading to the complete destruction of all matter in the universe. The Great Rend is a more speculative scenario than the Great Freeze, but it is a possible outcome if dark energy behaves in a certain way. If dark energy is what physicists call phantom energy, an extreme form of dark energy that grows stronger over time, the Great Rift could occur in the distant future, billions or trillions of years from now. The opposite of the Great Freeze and the Great Ripping is the Great Collapse, a scenario in which the expansion of the universe slows and eventually reverses. Instead of expanding forever, the universe would begin to contract, with galaxies, stars, and planets moving closer together over time. In the Great Collapse, the gravitational force of matter in the universe would overcome the repulsive force of dark energy, and the universe would collapse in on itself. As the universe contracts, temperatures would rise and galaxies would collide and merge. Eventually, all matter would be compressed into a single, incredibly hot and dense point, similar to the state of the universe just before the Big Bang. Some physicists believe that the Great Collapse could lead to a cyclic universe, in which the universe expands and contracts in an endless series of Big Bangs and collapses. This idea, known as the Great Rebound, suggests that the end of one universe could be the beginning of a new one, with each cycle creating a new set of physical laws and conditions. While the Great Collapse is a less likely scenario, given current evidence of the accelerating expansion of the universe, it remains a possibility if dark energy weakens or reverses in the distant future. The idea of the Great Rebound offers a more optimistic view of the fate of the universe. Instead of a single beginning and end, the universe could go through an infinite series of expansions and collapses, with each cycle leading to the creation of a new universe. In this model, the universe begins with a Big Bang, expands over billions of years, and then contracts again in a great collapse. However, instead of ending in a singularity, the universe bounces back and triggers a new Big Bang, starting the cycle all over again. The Great Rebound offers a possible solution to the problem of the ultimate fate of the universe by proposing that the end of one universe is simply the beginning of the next. In this model, the universe is eternal, with no definitive end, and each cycle of expansion and contraction could give rise to new physical laws, constants, and even new life forms. While the Great Rebound remains speculative, it is an intriguing possibility that challenges the notion of a linear, finite universe. Imagine standing on a distant planet billions of years from now, watching the universe approach its final stages. You see fewer and fewer stars in the sky as the galaxies get further apart and the light from the distant stars fades into the darkness. As the universe continues to expand, the temperature around you drops, and the once vibrant cosmos becomes a cold, empty void. Eventually, only the faint mica of white dwarfs and black holes remain, slowly radiating the last of their energy. In the final moments, even the black holes evaporate, leaving nothing but a dark, frozen universe. Time seems to stretch infinitely, without events, without light, and without life. This is the ultimate fate of the universe in the Great Freeze, a cold, silent end to the history of the cosmos. Alternatively, imagine the opposite scenario. The universe begins to contract, and galaxies collide and merge as the temperature rises. You watch the universe collapse in on itself, and in the final moments, all matter and energy is compressed into a single point of unimaginable density and heat. Then, just as everything seems to end, there is a flash of light, a new Big Bang, and the cycle begins again. The ultimate fate of the universe is determined by the delicate balance of forces shaping its evolution. Gravity pulls matter together, while dark energy pushes it apart. The interaction of these forces will determine whether the universe expands forever, collapses in on itself, or undergoes an eternal cycle of creation and destruction. As we continue to explore the cosmos and study the forces that govern it, we gain new insights into the future of the universe and our place in it. Even though the end of the universe is billions or trillions of years away, understanding its fate helps us appreciate the beauty, complexity, and fragility of the cosmos. The future of the universe is one of the most profound questions in cosmology. And while we may never know for sure how the universe will end, the various scenarios we have explored, the Great Freeze, the Great Rip, the Great Collapse, and the Great Rebound, offer intriguing possibilities for what lies ahead. Whether the universe ends in a cold, empty void or a fiery collapse, the history of the cosmos is one of constant change, evolution, and transformation. Understanding the forces that shape the universe helps us appreciate the delicate balance that makes life possible and reminds us of the incredible journey the cosmos has taken since the Big Bang.